Hi guys, and welcome to episode 4 of the Rocket Propulsion Masterclass series. Today is Werner von Braun's birthday, so what better time to start learning about rocket propulsion? In this episode, we're going to jump right in with talking about all of the various nozzle configurations. So, let's get into the episode.
By the time we get to section 3.4, George Sutton has given us all the mathematical structure that we need to do the preliminary nozzle calculations.
Right.
But as you'll realise from what I've said, there are a lot of idealisations that have taken place in that. And so he then starts to talk about nozzle configurations.
Right.
Now what's quite interesting is that once you get to sort of supersonic flow, then there are a whole lot of different nozzle configurations that you can consider, including, paradoxically, inside-out nozzles.
Aerospikes.
Or something else called a expansion deflection nozzle.
Is that where you have like a nozzle and then another nozzle on top of that?
It's got a skirt, so it's the flow is separated.
Right.
But do you remember, going back to this very important point about the flow being supersonic, you can do all kinds of things downstream and it doesn't affect what happens upstream.
Yeah.
So one of the things that you can do is chop off the nozzle away. So imagine that you've got an internally expanded nozzle,
right,
and you chop off of it away. Then the fact that this bit is missing doesn't affect what's going on down this wall. So I can basically take that side of the nozzle and put it over here.
And then the supersonic air flowing past the sides of the nozzle acts as the walls directing the flow.
Absolutely.
And as the air gets thinner, so you have the side of you have the wall here and the flow's going down there. There's supersonic air going this way, which acts as the other wall. As the air gets thinner, as you increase in altitude, I presume it expands outwards until you get an altitude compensating nozzle.
That's it. That's absolutely it. That's the
genius.
whole apparent beauty of plug nozzles. A few years back, a few decades back, Rocketdyne were investigating two-dimensional nozzles because they might have...
XRS 2000, I think, for the X31 project.
That's correct. And again, essentially what you've got is a nozzle that's been chopped in half, stuck back to back, and because, as you quite rightly say, the outside boundary is now formed by the atmosphere, and where that boundary sits is dependent on the external pressure.
But presumably at low velocities it's hideously inefficient because you need high velocity air to bring
Actually
the outside
not.
wall.
What happens is that although the flow is being constrained to follow this contour, which is turning faster than the flow would like, the actual shock waves being generated are very weak. And so what happens is that the flow sticks to that boundary. Now, this is a bit like you can do the experiment yourself. If you get a plate and hold it under the water tap, what happens? The water hits it and then it flows as a layer along the plate.
Okay.
And that's exactly what happens. In this case, it's the gas flow. And unlike the water jet, the actual outside boundary of the gas flow is determined, as you've completely correctly interpreted, by the outside pressure of the atmosphere.
Right.
And then as you go up in altitude, you get to a point where one altitude it's exactly matched. The flow is moving parallel, and the flow along that boundary is exactly what you wanted it to be.
Okay.
And then as you go up in altitude further, because the external pressure can't affect the supersonic flow field, the flow along the plate surface doesn't actually know about that. So at that point on, everything remains absolutely constant, and the external flow then continues to expand, but the performance of the nozzle remains constant from that point on. So by the time we've got to this, he's explained all of that, but then focuses on conical and bell-shaped nozzles, because although these are very exciting nozzle concepts, nobody really, there's been a few exceptions, but very, very limited, nobody's really managed to make these work to their advantage. And
the XRS 2000 and the RS 2000,
yeah,
as far as I'm aware, they were tested many times and worked perfectly on each test.
but one of the questions that you then have to ask yourself with all rocket engines is, what advantage did it give me? And the answer's a matched performance. But in terms of the structure of the nozzle and its weight, and also what looks like a very minor thing, but which I discovered very early in my career, you actually have to turn the flow towards the axis of a nozzle like this. And as a consequence, there's a little bit of area there that you lose. Because you've got to also get up to a Mach number of about 1.15 or something by the time it leaves the internal nozzle before it starts to wash along the external nozzle.
Right.
And that little bit of area that you lose is quite important because it's on the outside diameter of the whole engine. So it might not look like much of a width, but in terms of area lost that if you used conventional nozzles you could expand into, that's quite important.
Okay.
I personally have investigated plug nozzles for probably half a dozen different potential applications and never found an overall advantage with them. So from a scientific and technical point of view, they're very exciting, but whenever I've tried to actually apply them to anything, then they don't actually work.
What about on a, let's say, Titan or Venus, where you've got insanely high gradients between atmospheric pressure and sea level and vacuum? Would they be advantageous there, where you need nozzles that are?
I don't know. You've just given yourself a project, so to find out.
Okay.
But there is one area where this type of nozzle could be very important. So back in the 1960s, a guy named Phil Bono, who worked for Daedalus aircraft, came up with single-stage orbit vehicles, which used a complete base-filling plug nozzle. The most important part of that is that plug nozzle acted as the re-entry shield for the vehicle to come back. And so in that particular application, then there is an advantage for a plug nozzle.
That's brilliant, because you would need the walls of the plug nozzle to be very highly reinforced to take the heat of the exhaust jet.
Yes. And
so it would work very well as a heat shield.
And if you also introduce some flow through the combustion chambers during re-entry, you can control the vector, and you've got a certain amount of control over the vehicle.
So you can use the combustion chambers as like miniature parachutes around the base?
You can use it to control exactly. You've got the shock wave standing off the base of the plug, and what you must be careful of is it doesn't intersect the vehicle as the vehicle's coming down, and you can put some flow through the combustion chambers to give you a cool there.
So you're actually activating the engines, but at a low throttle setting, and so the gases act as a sort of boundary layer which protects the.
So you can
vehicle.
take that even further and put some flow through the base, and you finish up with something called an aerospike. And they're very, very interesting concepts. The problem with a vehicle like that, and as far as I can see, it would work beautifully, but and we're diverging from Sutton's book, but it's quite an interesting point, is that as the vehicle's re-entering, it can only pull something like 200 nautical miles cross range on the ground track, and therefore in terms of being suitable for commercial operations, you might finish up with your vehicle stuck on orbit for 2 weeks until the ground track comes within the range of the launch site you're wanting to put the vehicle back onto.
You would need additional very heavy wings on the vehicle, which would possibly negate the advantages of using it as a heat shield in the first place.
Yes, so immediately you put wings on, you change the name of the whole game. The whole point about these vehicles that Bono considered is that they were basically rocket vehicles which were then able to re-enter and fly back as a rocket vehicle and land exactly like SpaceX land Falcon 9 boosters.
Okay. So for anything other than equatorial operations only, it would be basically useless?
They would work for high inclination orbits. You've got to be very, very clever with the structures. modern composite materials and so on would make
Right.
these vehicles even more practical than they were. A lot of study went into them by the Douglas company. There was unfortunately a vehicle called the X30.
The Venture Star?
Sorry?
The Venture Star?
Yeah.
Or was that the X33?
That was the 33. The name of the vehicle escapes me for the moment, but this was a privately investigated vehicle by Lockheed, and they tried to do a nose first entry. But the trouble is the centre of gravity is all in the wrong place on a configuration like that. The beauty of Phil Bono's studies is that the centre of gravity was well aft and the vehicle was completely stable in re-entry, where the penalty is low cross range on the ground.
Right.
Whereas if you come in nose first, all the moments and everything acting on the vehicle are wrong, so you then have to put some sort of body flap on it or a drogue chute, and then immediately the cross range is coming back down to the 200 nautical miles. So we've diverged a lot from it, but that was really a discussion about the use of plug nozzles.
Right.
Now, when it comes to cone and bell-shaped nozzles, there's a good section in here in which George Sutton discusses the factors involved in that and how much thrust you lose. Remember that we said that in a real flow, as opposed to a one-dimensional flow, there's some divergence. Some of the flow goes off at an angle. In fact, some of the flow is going to go off in a 15-degree half-angle nozzle. Some of the flow is going to go off at 15 degrees. So you're going to lose that much axial momentum, and it's balanced out radially by the flow on the other side of the nozzle, of course. So you lose thrust. There's a simple calculation you can do for that.
Is it to do with cosine losses or sine losses?
Cosine losses. And so on a simple conical nozzle, there's a very simple relationship that you can derive, and you lose about 2% of the thrust. And it turns out that when you vary the nozzle angle, almost everybody reaches the conclusion that the optimum angle is 15 degrees. Now, that's only true provided that I don't infringe the separation problem at sea level. If I want the nozzle to run separated at sea level, I might have to come down as low as 10 degrees, which then leads to a rather long and heavy nozzle. And so, as a rocket engineer, you've got to do the calculation and see what maximises your payload. Whether a long nozzle with a lower exit pressure, better performance at altitude but a heavier nozzle, or whether a shorter nozzle, lose some performance at altitude but gain the performance at sea level. So there's a trade-off to do there. Almost everybody since World War II has concluded 15 degrees is the right number to have. I won't dwell too much on other concepts of nozzles. It's all very readable stuff. It's not mathematical, and based on what I've said, that's fairly straightforward.
Okay, so we think that's a good place to pause. We're going to stop here and pick it up the exact same place next week. In the meantime, make sure you write all of your questions down in the comment section, and we'll see if we can get around to answering them in future installments. See you next time.